This is an introduction to special relativity practice final exam. So let's go right into it. Number one, a spacecraft travels past Earth at a speed of 0.82 c. Part A, compute the Lorentz factor gamma. Part B, if 18.0 hours on Earth, if 18.0 hours pass on Earth, how much time passes according to a clock on board the spacecraft? And part C, explain physically why the two observers disagree. So we're given V is 0.82 c. Here's our Lorentz factor formula, that gamma is equal to 1 over square root 1 minus v squared over c squared, and we just substitute our 0.82, get 1.75 when we do the computation. I'm going to go through this quickly. Part B. Earth measures here, the change in time is 18.0 hours. The spacecraft clock measures the proper time. All we have to do here with this delta, delta here equals delta lowercase t over gamma. We get 18.0 over that 1.75, that 1.747. That's about 10.3 hours. So that change is 10.3 hours. So that's for letter B. And letter C, explain physically why the two observers disagree. Well, the spacecraft clock runs slower according to Earth because it is moving relative to Earth. Okay, so that's number one. Let's move along to number two. Let's see if this holds up. Oh, let me just take this off here. Okay, some humor. Okay, so let's see here. Let's get this in focus. We're good to go with number two. So a particle accelerator is measured to have proper length, 2.4 kilometers in laboratory frame. An unstable particle moves through the accelerator at speed 0.96 c. Part A, what length does the particle measure for the accelerator? So right here, L naught is 2.4 kilometers. Okay, so our speed is v equals 0.96 c. We want to get our Lorentz factor. We set that up. We get 3.57. Our length measured by the particle is L equals L naught over the Lorentz factor. So that's just going to be 2.4 kilometers over 3.57. You wind up with 0.672 kilometers. So the length, if you convert that to meters, is 672 meters. So that takes care of letter A. Letter B, part one, we want to know how long does the particle take to cross the accelerator according to part one, the laboratory frame. So the lab crossing time, what we do is that t is going to be equal just to L naught over v. So that's going to be 2400 divided by 0.96, okay, times speed of light, 3.00 times 10 to the 8th. And that's just going to come out to, right here, t is 8.33 times 10 to the negative 6 seconds. And if you want to convert that, that's fine to other units in terms of seconds, that's fine. And part two, particle frame crossing time. Now this is going to be the t prime L over v, 672 now, right? So that part A value we're using in this part B2, divided by same denominator in part one, and that's just going to give you t prime is approximately 2.33 times 10 to the negative 6 seconds. And part C, we want to verify the consistency using time dilation, so we use that t prime notation equals t over the Lorentz factor. So that t was 8.33 from part one of letter B, divided by the Lorentz factor found in letter A, and we do indeed get t prime. We get 2.33 times 10 to the negative 6 seconds. So the results for part C agree. So we're good with that. That's number two. Again, we're moving along quickly. Remember, this is supposed to be just a reference, extra study material for final exam in special relativity. So Number 3, we have two inertial frames S and S prime move relative to each other along the x-axis with speed v equals 0.70 c. An event occurs in frame S at x equals 1.80 times 8 to 10 to the 8 m. T is 1.20 s. Part A, find x prime. So, finding x prime, let's take a look at what we're given here. V equals 0.70 c, x equals 1.80 times 10 to the 8th, t equals 1.20 s. We could get the Lorentz factor, gamma equals 1 over square root 1 minus 7/10 squared. That comes out to 1.40. So, employing the Lorentz transformation here, x prime, that's going to equal gamma times the quantity x minus vt. So now in x prime here, we just substitute our values, substitute them, and then when we compute, we get x prime is approximately negative 1.01 times 10 to the 8th meter. Part B, we want to find that t prime for time. T prime, that equals the Lorentz factor times the quantity t minus vx over c squared. T prime equals 1.40 times, just substitute, 1.20 minus, for v, 0.70 c times for x, that's 1.80 times 10 to the 8th divided by c squared. Just performing some algebra and computation here, since vx over c squared equals 7/10 times the quantity 1.80 times 10 to the 8th over the speed of light, that comes out to 0.42. So for part B here, the t prime 1.40 times 1.20 minus 0.42. So we get that t prime is approximately 1.09 seconds. And for part C, determine whether the event lies inside or outside the light cone of the origin. Well, let's check the light cone. C times t, that product, plug in our values. 3.00 times 10 to the 8th for speed of light times 1.20, which is that t value. We wind up with 3.60 times 10 to the 8th meters. Since our product of c and t happen to be greater than x, we say the event is inside the light cone. So this is time-like. Inside the light cone would be the answer for letter C. Okay, so that takes care of number 3. Moving along now, let's go to number 4. Okay, so number 4 here. Whoops, sorry about that. Okay, so a probe is launched from a spaceship, moving at 0.75 c relative to Earth. The probe moves forward at 6/10 c relative to the spaceship. What speed does Earth measure for the probe? Okay, that's part A. So spaceship speed, let's do this. Spaceship speed, the velocity is 3/4 c. Probe speed relative to the ship, we'll say u prime equals 0.60 c, right? We're given these. So what we're going to do here is relativistic velocity addition. So we're going to say u equals u prime plus v over 1 plus u prime v over c squared. And we're just going to substitute. Substitute our values. We're going to get u as 1.35 c over 1.45. So we get that u is approximately 0.931 c. For part B, we want to know why is the answer not simply 1.35 c. Okay, so why aren't you just adding them together? So in this situation, what we say is for part B, it is not 1.35 c because velocities do not add normally near the speed of light. And we say the relativistic formula prevents massive objects from exceeding the speed of light c. Part C, we have here, suppose instead the probe is launched backward at 6/10 c relative to the spaceship. What speed does Earth observe? So here we have the backward launch. U prime now is going to be negative 0.60 c. So our u is going to be negative 0.60 c plus 0.75 c over 1 plus negative 6/10 c times 3/4. I'm sorry, 1 plus negative 6/10 times 3/4. So that's going to give you u is 0.15 c over 0.55. So our u there is going to be 0.273 c. So what we could say here, and what speed does Earth observe? Okay, Earth still sees the probe moving forward, but slower than the spaceship, and that's that again. That u is 0.273 c. Okay, now that takes care of number 4. Let's move along now. Number 5. Let's see what we have here. Proton for number 5. Okay, so for number 5, a proton has speed 0.94 c. Compute its Lorentz factor. So this could just, using Lorentz formula, we're given v is 0.94 c. M sub p is 1.67 times 10 to the negative 27 kilograms. Just substitute that in here. This would be y equals 1 over square root 1 minus 0.94 squared. So our gamma is, Lorentz factor is approximately 2.93. For part B, determine its relativistic momentum. Well, the relativistic momentum here is the momentum is equal to Lorentz factor times the mass times the velocity. So just substitute into each piece. Remember, we need our speed of light quantity there at the end, and this is going to be the relativistic momentum 1.38 times 10 to the negative 18 kgms. So, kilograms meters squared. And then here, total energy, we're going to use E equals Lorentz factor mc squared. Okay, so what we have here, E equals 2.93 times 1.67 times 10 to the negative 27th times 3.00 times 10 to the 8th squared. That's just going to be converting to joules. This is going to be E is approximately 4.41 times 10 to the negative 10th joules. And for part D, our kinetic energy, K equals our Lorentz factor minus 1 times the quantity mc squared. So very similar to total energy, and we just substitute our values and we wind up in joules. K is approximately 2.90 times 10 to the negative 10 joules. So that takes care of number 5. Okay, and moving along now to number 6. Okay, so number 6. Okay, we have a photon. Photon has wavelength 510 nanometers. Part A, determine its frequency. So we're given wavelength 510 nanometers. Convert that to meters. That's 510 times 10 to the negative 9 meters. Our frequency formula is going to be the frequency equals the speed of light divided by the wavelength. So we're just going to get F equals 3.00 times 10 to the 8th over 510 times 10 to the negative 9th. That's going to get converted to hertz at the end. And F is approximately 5.88 times 10 to the 14 hertz. Okay, part B. Determine its energy in joules. So photon energy, E equals HF. H is here 6.626 times 10 to the negative 34 joules. Here we have 6.626 times 10 to the negative 34th times 5.88 times 10 to the 14th from letter A. And now in joules, the energy is going to be 3.90 times 10 to the negative 19th joules. So that's all for the photon energy. For part C, determine its momentum. For the photon momentum, all we need as a momentum is the energy divided by the speed of light. So taking this photon energy here from part B divided by the speed of light, we get approximately 1.30 times 10 to the negative 27 kilograms per meter second. Kilogram meters per second. So part D, explain how a particle with zero rest mass can still possess momentum. Well, a photon has zero rest mass, but it still has energy. Since E equals that PC, a photon with energy must also have momentum. So that's the answer to letter D. Moving along, number 7. Let's see if this holds. Nope. Gotta put this up. Number 7. Okay, so for number 7, a distant galaxy emits light with rest wavelength. Lambda sub naught is 410 nanometers. An observer on Earth measures lambda equals 615 nanometers. Is the galaxy approaching or receding? So for part A, here's what we're given. That lambda naught equals 410 nanometers. Lambda is 615 nanometers. So we could say since the observed wavelength is longer than the emitted wavelength, the light is redshifted. So the galaxy is receding under those circumstances when we compare these quantities. Part B, determine the recession speed as a fraction of c. Well, for part B, we use relativistic Doppler formula for recession. That's going to be lambda over lambda naught equals square root of 1 plus beta over 1 minus beta, where beta is the velocity divided by speed of light. So here we calculate the wavelength ratio. We're going to get lambda over lambda naught equals 615 over 410. That just gives you a 1.5. Squaring both sides, doing some math here, computation, 2.25 is 1 plus beta over 1 minus beta. We're going to solve here for beta. Beta is, when it's isolated, approximately 0.385. So that would mean this velocity is approximately 0.385 c. Okay? And for letter C, explain the physical origin of relativistic redshift. Well, for part C down here, the wavelength increases because the source is moving away. So successive wave crests arrive farther apart in time. So that takes care of number 7. Moving along to number 8. Okay, so we have 2 events here with coordinate differences. Here's our delta x equals 900 meters, delta y is 0, delta z is 0, delta t is 2.0 times 10 to the negative 6. A, compute the space-time travel, s squared equals c squared, delta t squared minus delta x squared. So we just take what we're given and substitute it into the formula for this space-time interval. Okay, here we want to find c delta t. C delta t is going to be 3.00 times 10 to the 8th times 2.0 times 10 to the negative 6th. Okay, right here. We're going to get 600 meters. And then we just substitute. We get 600 squared minus 900 squared. That's negative 450,000 meters squared, which we can convert to negative 4.50 times 10 to the 5th meters squared. So that's part A. Part B, determine whether the interval is time-like, space-like, or light-like. Well, since s squared is less than 0, the interval is space-like. And for part C, can one event casually influence the other? Explain. Well, we can say here, due to the separation in space being too large for light to travel between the events in the given time, one event cannot casually influence the other. Okay? So that answer, that'd be no. And that's for number 8. And then we move along into number 9, and this is the last one for our Introduction to Special Relativity Practice final exam. So let's just get this in focus here. Okay. Twin A remains on Earth. Twin B travels to a star system 12 light years away as measured in Earth's frame at speed 4/5 speed of light, 4/5 c. Immediately turns around and returns at the same speed. Part A, how much time passes on Earth during the round trip? So, part A, the distance to star and Earth frame, that would be 12 light years, right? Now our speed is v equals 0.80 c. So our one-way Earth frame time travel, T over L over V, that C equals 1 light year per year. And our lowercase t here is 12 light years over 0.80 C, that's 15 years. So the round trip, and that T sub Earth, that's going to be 30 years, okay, for T sub Earth. So how much time passes on Earth during the round trip? 30 years. Okay, so now from here, letter B, how much proper time passes for twin B? Okay, so Lorentz factor, calculate that. That's 1 over square root of 1 minus 0.80 squared. That's 1.667 approximately. So twin B's proper time, that would be that T sub Earth over the Lorentz factor would be the 30, that round trip time, over 1.667. So that is going to be for the twin B, 18 years. Part C, which twin is younger upon reunion? Well, twin A ages 30 years, twin B ages 18 years, so twin B is younger by 12 years. And for part D, explain why the situation is not symmetric. Okay, the situation is not symmetric because twin B changes inertial frames when turning around. Twin A remains in approximately one inertial frame, while twin B accelerates and reverses direction. All right, so that's the practice exam for Introduction to Special Relativity. 9 problems, and hopefully this helps as just a supplement to study. Thank you, and have a great day.